All right. So we are correct the last homework. So now we're working on the question number 13. All right. So I hope that the physical picture is clear. So initially we have just like a rope. There's a weight mass is hanging over there, right? And then there's like a force. It's a pull up rapidly, right? If this force is really large, and they will break the rope, right? And obviously at that point, that critical point, it will generate the maximum acceleration up. Is that clear? Yeah, so this is how they get. We're starting from the free body diagram, and we analyze the box, or is it the block? Okay, and we got this equation based on the second Newton's law, and then we get a mass of the block based on the weight of it, and we got is 3 kilograms, and T is the maximum tension on the rope, and we can get the maximum weight. Okay, all right. Any other questions? Number 18. Let me check the question number 18. All right, so we have a 4. The velocity is so proportional to the t squared. The parabola graph is the graph of the speed v as a function of time for an object. Which of the following graphs best represent the maximum F of the net force? Oh, it's since v is proportional t squared, right? And the acceleration is, well, it's the change of v in the unit time. So acceleration is proportional to well, it's like t. Yeah, even this one, well, it will be pretty easy to describe that in the derivative. That. So because v, a is the derivative of v. So we just take the derivative of v t squared, and that gives you like a proportion of t, right? But if you don't learn the basic calculus, you can picture that since a is defined as the change of v in the unit time. So yeah, you can still work in that way. You just find out t1 square minus t naught square and divide by delta t, right? And that still give you like the change of like it's like linear relations, right? Based on that, we can get your acceleration is proportional to the linears of the time, right? And based on that, it's only a is yeah. So after we got a is proportional to t, and f is obviously is proportional to the accelerations, right? Yeah. So f should be linear, proportional to the time. Okay. All right. Any other question on other to other student remotely? No. Okay. Great. Later on, we'll do a short in-class practice, but before that, we're going to review, like finish up the questions in the last class. We finish up this question, right? And the poly, right? How about this one? We done with that, right? Okay. How about this one? No? Okay. All right. So continue on the question on last package. So number 4, assuming that you did that at home, right? You didn't. You need a couple minutes. I give you a couple minutes. Okay. I don't believe that everyone on the other end is ready finished that. So give you another couple minutes. Okay, someone said missed the first 2 class. Okay, for any reason. Okay, so I already passed the link to the recording to Jason. Do you know Jason? Yeah. So the center staff should have the video recording. You can just study by your own. If you, for any reason that you missed some of classes, we do record all the classes. And in the first class, I give everyone a link to the Google Drive. So all the material I sharing here will be put in this, including the homeworks. So I will find it out and share it in the Zoom again later. All right. So this is a question assuming that a poly is a frictionless and massless, right? So which also means that we don't care about the rotational motion of the poly itself, right? So if the surface of inclined plane is frictionless, determine what's value of theta will cause the box of the mass m1 to accelerate up the ramp, slide up the ramp at a constant speed. All right, I will show the answer first. So both of them is actually pretty close. So that critical angle theta should equal to inverse sine of the ratio of mass 2 over mass 1. You got it? Okay, great. So yeah, so we can just do the free body diagram and this object's moving upward, right? Yeah, so it's like going up. So based on that, I can define mg 2 minus m1g sine theta should equal to m1 plus m2a. Yeah. I write this equation. Does that make sense to you? Why I write this equation? I consider M1 and M2 as a system. You can do that, even it's not. It's kind of weirdo system. Okay. I can still consider that as a system, just like the question we did before, right? So since they move together, so they share the same acceleration. Even while since it's like the shape is changing, so for the different part of the system, the direction of acceleration is changing, right? It's changing, but the value has to be the same, right? So this one have acceleration downward, and this one have this M1 is have an acceleration that's being accelerated upward. Even both of them have a different direction, but the value, magnitude has to be the same, right? Otherwise, it cannot move altogether. But in that way, I could consider, oh, this system, they have a they have force M2G, right? And what else? They have a, yeah, this one is pulling down. And on the other hand, a portion of the weight of M1, like in this direction. So this component will drag the system backward, right? So the net force will be the expression on the left, right? And that makes the system M1 plus M2. This is work as a system, right? And move in the same acceleration, right? So this is also an alternative way, but you can still break it down and do a free body diagram for M1 and M2. It should give you exactly the same result, but I prefer this way. Yeah, because things sync them in the system will take some time. Okay, and based on that, I can get a M2 minus M1 sine theta over M1 plus M2G, right? So you just rearrange it. And yeah, so to make A, so accelerate upward, so which means the A has to be a positive, right? A has to be positive as we define this way. So M2 minus M1 sine theta should be a positive value. And that leads to this result, theta should less than sine -1 M2 M1. So part 2, slide up the ramp at a constant speed, which means A has to be 0, right? It just moves constantly. So your theta, we set A equal to 0. So the numerator must be 0, right? Numerator must be 0. So theta is exactly equal to this value. Okay. All right, part B. If the coefficient of the kinetic friction between the surface inclined and the box of M1 is mu k, derive an equation satisfied by the value of theta, which will cause the box of mass M1 to slide up at a constant speed. Okay, when it slide up the ramp at a constant speed, which means it's in the equilibrium, right? A has to be 0. So we just set all the forces, external forces to our object, set it to 0, right? Yeah. All right. So I just write it here for part B. So we can do I'm just using another colors. Which one you prefer? I know it should be easy to read. Purple. Blue. Okay, blue. Yeah. So since it slide up, right? It slide up. So which means the direction of the kinetic friction must be opposed, right? Oppose the direction of motion, which means it has to go this way, right? It has to go this way, right? Because it's slide up. This is how you define direction of friction. Okay. Also, they have a M1G, okay, and normal force perpendicular to the interaction surface, like that. Okay. All right, and tensions here. Okay, so we can get T minus M1G, and doing the trig, it should be sine theta minus, this is like a mu k n, right? N will be the normal force, right? And that will be another component of the weight. So M1G cosine theta equal to 0. And this T, since it's in equilibrium, so this T is actually balanced with weight, M2G, right? So this is for when you analyze with M2, so we have a T and you have a M2G, right? So these two should be balanced, all right? And that's it. And then you just plug in and this should give you a result that sine theta plus mu k cosine theta should equal to the ratio M2 over M1. Okay? Got it? Okay, cool. All right. So this question, well, after you analyze the right object, and this is actually the first part is have acceleration. Second part is that move in a constant speed, which means a equal to 0. After you figure out that, rest of it should be pretty easy. Clear that. Move on to next questions. Yeah, circular motion. Yeah, we mentioned that. Okay. Question number 5. As well, I'll give you another 2 minutes. Oh, another student asked how to view the recording. Okay. How about that? I also put a page in the shared folders. I didn't do that yet, but I will do it after the class, and we'll post all the links on that page. Okay. Yeah, I really share that to the center staff. Probably didn't. You can just ask for it, but I think that would be more efficient too. Where's the link? I said I will share. I will post that on the page in the share this drive later. Okay. Okay. Oh, sorry for that. Okay. All right. It's okay. I will post this in the shared drive. All right. Let's focus on these questions. So we have a roller coaster enter the circular loop. At the very top of the circles, the speed of the car is 25 meters per second, and the acceleration points straight down. Okay, so if the diameters of the loop is 50 meters and the total mass of the car is 1,200 kilograms, so find the magnitude of the normal force exerted by the tracks on the car at this point. Okay, I'll show the answer first. The answer is 1.8 times 10 to the 4th Newton. Get it? Okay, cool. Yeah, this fraction actually is pretty easy. So you just go through it pretty fast. So we have a loop, right? So this is a car upside down. Like go this way. Okay, do the free body diagram. We have a weight. It's starting from weight, right? And have a normal force. Since this is upside down, so the normal force is pointing downward as well, right? So we have two forces pointing to the centers. And these two forces, or say the vector sum of these two forces, act as what? Centripetal force, right? Centripetal force should equal to mv squared over r. So you need to find out the net force first and set it to the centripetal force, mv squared over r. Okay, and then you just simply solve it. And you plug in number, it should give you answer very quick. All right, so this question is pretty easy. All right, next one. Just oops. Okay. Someone don't have the shared drive. Okay. Let's finish up this question first, and I will share that link to everyone. Okay. So this is a type of horizontal circular motions. All right. So do the free body diagram. Weight, normal force. All right. So yeah, what's the direction of the net force? Should point to the center, right? The center is somewhere here, right? Because it's doing the circular motion like this way. This is like the circular path. I don't have a space here, but actually you can just well, I cannot go across the window. But, yeah, yeah. So this is the center of this circular motion, right? So your net force, which is the centripetal force, should pointing downward, right? So that is actually give you how you just do the vector sum. So for these two forces, you should project to that direction. All right. Okay. So we can analyze starting from first in the vertical direction, in the y direction, the normal force times cosine theta, minus mg equal to 0 because vertically there's no motion. In the y directions, n time sine theta, and that should be your centripetal force because the weight don't have any contribution horizontally. Only the portion of the normal force act as the centripetal force, and we square over r. Right? Just doing that, we have a system to go. and you solve them, you should get tangent theta equal to 1.59. That give you theta is 57.8 degrees, something like that. And also n mg over cosine theta approximately equal to 4.6. Hold on. Yeah. Yeah, it's just like continue, finish that first. Okay, so it's 10 to the fourth newtons. Yeah, I was stuck because this question is not very good for the values given. You really should have a consistency on the significant figures, right? Like this one have a 2 and speed of that, and this one have a 40. Yeah, usually it will be right into 40.0. In that way, you have a 3. And then we can keep into 25, right? But in this case, if we want, consider it's a fraction AP Physics 1 test, so we should keep your significant figure as 1, right? Yeah. So keep the least significant figure. So in that way, your the angles should approximate to 30, and this one is actually approximately 5 times 10 to the fourth, like that. Okay. Yeah. What? Actually, you will. Yeah. So you need to check your answer to keep the least significant figures given in the data. Yeah. Yeah, like a 40 only have one significant figure. 0 doesn't count, right? Or integers, last one does count. What? Why is the angle? Yeah, that's as I said. You got this value and you need to just rewrite into 60. 60 only have one significant, right? Yeah. And this one also 5, just one, just count one.
Oh, wait, where could we pull this up? Because, like, I want to pull it up on my computer.
Someone saying anything? I cannot hear you.
Where could I, like, is it in the drive right now? Because, like, I'm not sure if I have it, and I want to see if I can pull it up.
Could you repeat that?
So,
Yeah, sorry, I just turned on the value, my values. Could you repeat that?
like, where in the drive, like, where's the drive? Because, like, I want to see if I can pull it up.
Oh, the documents?
Yeah.
Oh, yeah, I just said, like, after finish these questions, I'll just share the link one more time, okay? But for this
Like,
question,
yeah, but, like, because,
do you
like,
have
I'm,
do you have any question in this question?
because, like, I might leave soon, so, like, I want to, like,
Oh, okay,
is there a way to
okay,
get the
okay.
link?
Okay, cool. But all others, do you have any question this? No, right? Okay, I'll stop sharing this. Should be somewhere. Yeah. All right. Do you got that link? All right, so far I pulled all the material for the first 2 weeks, and sorry. Yeah, also the material going to use today as well. All right, great. Okay, assuming there's no more question on this previous package, right? All right. Somewhere. Oops. What's happening? All right. Hope everyone have that access to that shared drive. Okay, so if you go through, click into it on the Wednesday, I'm sorry, on the week 3, there's a practice in the Newton's law. Yeah, so we're going to do it now. So I just give you, here we have, well, sorry. We have 8 multiple choice question. I'll give you up to 15 minutes. Yeah. Luckily I have a hangout for you guys. Double-sided. Oh yeah. Yeah, we are doing this one. But you can easily find out from the link I shared it to you. All right, guys. So if you finish that, we'll have a 5 minutes break. I will correct it after the break. All right, so here are the answers. So first, B, A, B, C, 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 A. All right. All right, any questions that we need to discuss here? Number 3. Mark it out here, number 3. Anything else? Huh?
I have a lot.
A lot.
I answered first.
Am I using the right? Hold on. Okay. Yeah. I'm afraid I'm using the right key. All right. So for you guys, what's the problem you're going to discuss? Number 6 and number 7. Okay, number 6 and number 7. And mark it out. Wow, it's a lot. Didn't realize it's a very difficult practice. Any else? So we have 3, 6, 7. 3, 6, 7. Yeah. Any else? All right, I'll just switch back to the questions. Where are the questions? No. This one. Yeah. Okay. All right. So the sub question here. Number 3. A pump with a mass of 0.3 kilogram is sliding along ice that can be considered frictionless. The pump's velocity is 20 meters per second. The pumps now cross over onto a floor that have the coefficient of kinetic frictions equal to 0.35. How far will the pump travel across the floor before it stops? All right. This question even is using the energy to solve, which is even if we don't discuss this, we're going to discuss it today. But this questions, I believe you will learn that at school, right? So, well, using the energy to analyze it will be much easier. Let's say initially they have a kinetic energy, right? So before the pump reach to the surface with the frictions, so they have a kinetic energy. And it's how far will the pump travel across the floor before it stops? So when it stops, the speed equal to 0, right? So they have a kinetic energy change, and that one is equal to what? The work done by the frictional force, right? Yeah, so if okay, we have a question. We have a question here. Number 4, okay, another question. Yeah, basically the work done by the friction equal to the change of kinetic energy. So that will be the change 0 minus what? Initial, right? mv squared, right? And the work done by the frictional force should be the work. The work done by the frictional force times the speed of travel, right? That is the work done. So that one, the frictional force equal to what? Equal to the equal to the mu k n, right? And n is mg, so it's mu k mg. Okay, and yeah, we're about to start that. So it's not start. Let's say this one time that, so that actually, because the frictional force is opposed to the direction of motion, right? So that usually is they have a 180 degree in between, right? So will be mu k mg time the distance time cosine 180, which is -1, right? And that should equal to -half mv squared. So this part we know the mass, right? Yeah, we know the mass, we know the initial velocity. This one we know, and mu k is giving, yeah, mg is known, so we can figure out the s. Okay? That makes sense? Any question from this equation? Yeah, any question from this equation? So nope. Okay, good. All right, so this is number 3, right? So you just simply plug in and you can solve it. Let's move on to number 4. So we have a string with a stiffness constant K. It's like a spring constant, right? 50 Newton per meters. So we learned that the restorative force equal to negative kx, right? So that k is the spring constant. Have a natural length 0.45 meters. It is attached to the top of the incline. That make a 30 degrees angle with the horizontal. The incline is 2.4 meters long. A mass of 2 kilograms is attached to the spring, causes to be stretches down the incline. How far down the incline? That's the end of the spring rest. Okay. First, after we need to get a clear picture of what's going on. So first, we have incline, which have an angle is 30 degrees, right? Yeah. And at the top, it's attached with a spring. And this hung over a, what was that? Is I think a ball, right? Yeah, or something, right? Yeah, a mass of 2 kilograms is attached, whatever it is. So we have a mass. So this one is attached on the string. Okay, so okay, let's redo that. Reader. Let's draw this way. Initially, they have a natural length, maybe this much, right? But after the spring has been attached by a mass, so it has to be stretched out, right? Has been stretched. So now the length is reached out to here, correct? Okay. So they actually ask you about this distance, right? They ask you about this distance. Let's say delta x. But at this moment is at the end of the spring rest. So it just stop here. So we can do the free body diagram with this mass at this location, right? Because we know it stay at rest, which is reach the equilibrium. All right, so we have weight, normal force, and what else? Restorative force on the spring, right? On the spring is draw back. It have a tendency go this way. So that's another force, right? And basically just that, right? So this is, we have 3 forces balance each other's. And well, we can consider that along the direction of the incline, so the net force will equal to 0. This actually not move at this location, right? So we can see the restorative force, which equal to negative k delta x, should equal to what? So this one is actually shows the direction which is against our definition is point back, right? Plus the component of the gravity, which is mg, I believe it's sine x, sine theta, right? Sine 30. So that should equal to 0, right? I think it's just that simple, right? So your delta x should be mg sine 30s over k, right? Yeah, we this is how we just started said, does the end of the spring rest? Because that is a key word, rest, which means that it's in the equilibrium at that location, right? All right, so since then we can just analyze at that location, do the free body diagram, right? Yeah, hope you still remember the steps we introduced in the last class, right? So analyze like what's this the stellar motion and figure out which is your object to study and working from the free body diagram. These all the forces act on the object at that moment. Okay, and after that, what you can split into different directions and use the Newton's law to analyze it. Right. So we actually follow that x-axis. Make sense? Yeah, because we don't care about the vertical direction because there's no motion at all. Only is that x direction is fine. Okay, so really? Half?
You add it to the probably
Hold on, I need to do that. So sorry, I did this a while ago. It's like about 10 over. Oh yeah, so you need to add the natural length. Here it just said a change, right? Well, it said how far down the incline that's the end of the spring, right? So from the top to the end, right? So we just got the change. We need to add the initial, the natural length, okay? Yeah, after you got this, you just plus 0.45 meters. All right, cool. Next one, it said number 6. Anyone have question number 5? No? Okay, good. Number 6 here. A force of 20 newtons acts horizontally on the mass of 10 kilogram being pushed up a frictionless incline. That make a 30 degrees angle with a horizontal. All right. All right. So obviously that. Obviously, we need to analyze with the block here, right? So, starting from the weight, right? The weight, mg. What else? Normal force, right? And this force, I just draw from the center, F, right? Yeah, I think this is the 3 forces act on this object. All right, and then what? Yeah, we just analyze one by one. So in the different directions. So starting from, since it's be accelerated upstairs, right? Up the hill, up the incline, push up the incline. So we define that this direction of A, right? Will be accelerated that way. So this is your X, and this is defined as your Y. And then in the Y directions, I can do what? Normal force minus the component of the gravity. Component of the gravity. So that should be cosine, right? I believe. Yeah. So cosine theta. So that should equal to 0. Okay. Oh, and also the F also have a contribution to that. Right. So F also have a contribution. So that is x direction, y direction. In the x direction, we have what? F times cosine theta minus mg times sine theta, right? So that should equal to ma. Well, they asked for the magnitude of acceleration of the mass up the incline. So they just asked this a, right? So we have a f times cosine theta minus g times sine theta. Since we know the force over m. Yeah, since we know the force, we know the cosine theta. So actually, we just need to vary about the x direction, right? And that actually give you the acceleration already. Yeah, so you simply plug this in, and that should give you the answer C. All right, is that clear? All right, let's keep moving. Next one, number 7. Okay, according to the diagram below, what is the tension in the connection string if the table is frictionless? All right, so we can start to, that's the way I analyzed before. Since they move together, so I can consider both as like both blocks as a whole system, and it'll be dragged to the right, right? So you can picture in this way. So I define this is M1. It'll be easier to using the sample first, and this is the smaller one is M2. Okay, do that way. So I can firstly get the equation F minus M1. Sorry, M2. Yeah, sorry, this is M1. This is M2. But either way, I just follow my equation. So M1G, does they have a M1G, drag this back, equal to M1 plus M2A. So that's give you the first equation to get the acceleration of the system. Yeah, I plug in, I got this one equal to 0.067 meter per second squared. All right, then what? Yeah, then you can just analyze with this block, right? So tension on the rope will be T. T minus M1G should equal to M1A, right? And that can give you the tension. Yeah, which is this value. Right? So this M1 you need to plug in 2 kilogram. Okay. Yeah. So you can find out the benefit if I consider M1 and M2 as a system, right? So that can give you the status of the motion of the system first. After you got A, yeah, you can analyze with the M1. You can analyze with M2 either way. But after that, it would be very easy to get the answer. Okay. Any other questions for this practice? Eight? No. Answer 8 is 8. First one. All right. Well, we do not have too much time today for a new package, but let's start it. Stop sharing. Let's see where I put that.
He wants us to do work right now.
Great. All right. So this is the new package. We have those on. Yeah, right. Okay. So let's go over that pretty quick. All right. Work done by a constant force. So, well, so you can see that some question, especially have the forces involved. If you analyze from the respective of energy, that can make the question much easier. So first is the work done by a constant force. So we know the work done by a force is not a vector. Okay, the work itself, I don't have directions, right? But the force, like say, we have a force just makes the object move in some directions, and the angle between the force and the displacement is actually matters or effect to the work done by the forces. Right. So here the work is defined as the what? The dot product of the force and the displacement. Yeah. So it's if the force is in one direction and the object on which the force is working is displaced in a certain directions, and only the component of the forces in the direction of the displacement does work. Yes. So this is mean that if you have a for instance, we have an object here, and this move in that direction, and with the displacement s, okay, and your force, if it's a line, like for instance, this is still force is pointing this way, right? So only this component, that will be the F parallel, and only this component in the direction of displacement does work. And the other component perpendicular to it doesn't work, right? This is actually we have. So this F parallel is actually F times cosine theta. Yeah. All right, so this is a pretty basic idea of the concept of the work done by a constant force. All right, so here we have a very basic questions. I try it. Give you a minute.
I'm coming! I told you this like 3 times. Okay, now I'm downstairs. This is the second time I see this. Yesterday I see this one. It's wasting. Okay, mommy, I have to show my fault.
你要是可以，你跟我们讲，我们会消灭你。
多了，他让我打你。Yes, but that's the one you trust. Mommy could have got to eat and you always did. She's always chemical, 所有都是在上面。对。但是我要打你的，我要猛打你的嘴巴。
你要是跟我们讲，我们会消灭你。如果因为脱你，
这个你看到没有？Mommy take home, purposely, for my current call. 这个 animal, yeah. Okay, got it. I got it. Keep saying. Are you animal? You're behaving. Mommy, do it. Cannot do this. You know your fear. No.
No, I just don't want to get any questions crazy.
就是要打死你，是第这，我知道我没打你
Crazy.
你是 twice，你还到别人 crazy， 你还要上别人 crazy， who is crazy？ Who？
Be quiet.
All right. All right. All right. So we have incline. The incline angle is 40, and we have an object. Oh, there's a typo, a mass O. All right, so from the top of the incline and finally it reached to the bottom of here, right? So the displacement is 8 meters, right? Yeah, so this is actually the X, right? So they want to know how much work done by the gravity, right? So gravity is here. So as we mentioned, it's only the component of the force along the displacement that's work, right? So in this way, we need to find out this component of the gravity. So the work done by the gravity should be what? Should be mg, and that's give you sine theta times the displacement d, right? So the whole displacement. Yeah, so that should give you the answer. Plug in, just write out the answer. It should be 17604 something. Part B, how much work done by the normal force? Normal force is perpendicular to the surface. On the other hand, it's perpendicular to the displacement. So, well, 0, right? So that component doesn't work because it's perpendicular all the time. Part C, how much work is done by the friction? Okay, friction, frictional force. So the force itself, so you can do is frictional force times B, because frictional force is pointing this way, right? And your displacement is opposed to it. So they have a cosine 180 in between, which is a -1. Okay, so negative Fk times D. Fk is what? Mu k times n, right? This is what they go. So be negative mu k. N can be got from the other component. N will be balanced with the other component of the gravity. There's mg cosine theta times d, right? and I give you another negative 630 joule. Okay, what is the total work done? Sum them up, right? Sum them up. Okay, the answer should be 1130 joule for the total. All right, so this fraction, pretty basic, but to give you ideas that how the work done by a constant force. All right, move on. The work done by a varied force, like the actual force is not always constant, you know, right? So if you know about the calculus, is this work done.
你来这个学习中文
So
课
the
看英语
official
就是说呢
definitions
表
work
个
done,
但是
as
文
we
化课
said, is what is in the for the constant force is defined as a force times the x, right? But the f might be just a function, right? Function of x. So in that way, but this one, it will be defined as the integral. Oh, that's
What?
What do you actually?
What did you think of the Chinese test? Phil?
I don't think I made Chinese.
should be WX.
The reading
Did you get a
course,
did you get a writing
So it
portion?
will be
Yeah.
from
Did you fill it
S1.
out or you left it blank?
it did like 20.
So that like consider f as
Oh.
a function of your
You wanna get Chinese,
displacement.
you have to get
we
at
can
least
define
zero
this one.
characters.
Yeah, but without learning about the integrations,
So I already
so
made it.
basically the integration show you the what?
That's for the writing.
Area and the curve, right? So you have
What
a
did you get?
there is that f is a
How many what?
function of s about s. So
I
this
just
f will be
remember me at the
varied,
time
any
when me
shape
and you
like
were
that,
under
right?
it.
So when we
Yeah, but how
doing
do you
this
rate?
integrations,
In
it will be
opinion.
integrate from one point to
Yeah.
another point. But that actually give you the
No,
area.
but
So
like-
this one
What's the
on the graph is equivalent to this, right? So we only need to know that.
But I didn't
We
know how
only
to
need
write
to know
the
that because
entire
AP
writing.
Physics 1 don't need a calculus to solve the question. But if they give you a test, we
What did
just
you
need
think
to
of the
know.
reading part?
Okay, the work done by a varied force should be the what? Area beneath the curve. That's it. We just need to know that. All right, so next question, just directly using this this technique. Oh, someone talking? I didn't realize that. 'Cause
I want Lian.
你这个西红柿炒蛋是怎么？
okay, great. Sorry for that. What's going on, Alan? Okay. All right, so this question, find the work done by the force F on the object as the object move from 0 to 9 meters. Okay. All right, so as we said, the work done, it should be the area underneath the curve. So it should be the area of this trapezoid, right? Right, for physics, but trapezoid, the upper height is from 3 to 6 will be 3. And from here to here, the bottom is 9. The area of the trapezoid, half time 3 plus 9 and 4. 4 is the height, right? It's just that. I believe it's 24 joule. Yeah, just that simple. Find out area of that trapezoid. Find out the speed of the object at x equal to 9 meters. How do you do that? Well, we need to using the one that's introduced in the nest, as work energy theorem. We actually discussed that. So the total work done should be what? Change of kinetic energy, right? Yeah, so sense is, I believe it's that, yeah. So the item start from rest. Initial velocity should be 0. So we just need to vary about the final velocity. And this is the final kinetic energy is minus initial, which is 0. And that should be the work done by the force totally, which is 24 joules, right? That's you can get the final speed, which is I got a root of 24, which is roughly about 4.9 meter per second. Okay, yeah. Keep moving. All right, this is the one we mentioned. The total work done should equal to the change of kinetic energy equal to that. And this total work done could have a lot of like all the forces act on the object. We have a different portion, as I mentioned in the first question, right? The gravity can doing the work, and the frictional force can doing the negative work, right? Or they may have some other external forces act on the object, or restorative force. All of those can doing a part of the work to the system. And we sum them up, and that give you the what? The total work done. Okay. And next one, the gravitational potential energy. So, which is the negative of the work done by the gravity. You can define that way. So it's potential energy. So delta U. So the change of the gravitational potential energy should equal to the negative work done by the gravity itself. Yeah. Okay. As we don't have too much time, let's finish up the next two questions, and maybe we'll just call it the end of today. So let's do 2 more here. Okay. Oh, someone write, what does this mean? 31/2 revolution. It's a, well, it's just like we have a circular path. Yeah, it's just a half of that. So from this point all the way to here, right? This is how the 31/2 of revolution. One revolution is completing a circle, right? Yeah, so first question, what's your answer? A, wrong. Sorry, it's not A, definitely not A. Yeah, someone got it. Henry, good. C, 0, why? How much work does the centripetal force? What's the direction of centripetal force? Pointing to the center, right? What direction of motion? That way. Be very careful about the circular motion. Any point that your centripetal force is perpendicular to the direction of motion, right? No work done. No work done. Or you can analyze with what? You can analyze with the energy point of view. So for any point, the speed is unchanged, right? So which means the net force, or say the kinetic energy is unchanged. If the kinetic energy is unchanged, the work done, and it's only the centripetal is the net force, right? And it doesn't work, right? It doesn't work. So any point, it doesn't work. Oops. So yeah, let's mark it. Option here is C. Second one, which is your option? D. Yeah, this one you got it. Yeah, this one is not hard. Like it's a plugin. So the work done mg sine theta time what? And I know it's length L, right? And that should equal to the change of kinetic energy, right? Right? You just plug in and that should give you the answer. So V is 7.7 meter per second. Okay. All right, great. So let's say today, hopefully you learn well, and well, it's look like you do need more practice. Right? Okay, cool. So the student here in center already have the homework, and for your guys on the Zoom, I will post it later, maybe in a few minutes. Okay, and you should already see Google Doc, and I share the link of the previous video recording in it. So everyone should have the access to it. Okay. All right, great. So do the homework, and you can finish up the last few questions in this package as well. All right. See you next time. Bye. Yeah, someone is still asking about the link. You can just scroll up and just show you the link, and I just replace that here. All right, do this again. Hopefully that works. All right, see you next time.